The Cigar Galaxy blazes with furious energy, forging thousands of stars at once, a true cosmic starburst. But what drives this incredible galactic furnace, and what can it teach us about the life of galaxies? Join us as we explore one of the universe's most dazzling factories of suns. If you enjoy this journey, please subscribe and share, and tell us in the comments which galaxy fascinates you most. Thank you for watching. Now let's begin. Far beyond the quiet edges of the Milky Way, the Cigar Galaxy takes its place in the larger structure of the universe. It lies in the northern constellation of Ursa Major, just beyond the reach of the familiar Dipper stars that mark the night sky. When astronomers describe this system, they point out that it is one of the most prominent members of the nearby universe, visible with small telescopes and striking in larger instruments. In shape, the galaxy is elongated, tilted toward our line of sight, which is why it carries its popular name. From Earth, it appears like a spindle of light glowing softly against the darker backdrop of intergalactic space. Its distance of about 12 million light-years means that every view we have of it is already an ancient record of its past. The light we now see left the galaxy when early human ancestors still walked upon Earth. This system is not alone, but belongs to a wider collection of cosmic structures. Astronomers often describe galaxies not as isolated islands, but as members of groups and clusters bound together by the long reach of gravity. This one is among the closest bright galaxies outside our own group, situated not far from the grand spiral M81. Together they form the heart of what is called the M81 group, a small family of galaxies bound in gravitational relation. Interactions between these members shape their evolution, producing tidal streams, distortions, and transfers of material. These relationships are important because they help explain why this galaxy appears so different from a calm spiral. While our Milky Way shows wide open arms of stars, this elongated system has been stirred into more chaotic motion, and its core bursts with activity. To understand it, it is necessary to picture not only the stars and gas within, but also the space surrounding it. The intergalactic medium, though tenuous, contains thin strands of gas that stretch between groups of galaxies. On the scale of millions of light-years, this galaxy appears as a bright node in this web of matter. Gravitational influences extend across these vast distances, and the group members gently tug upon one another, setting the stage for encounters and disturbances. Its position at the center of a gravitational dance ensures that it is constantly reshaped, drawing in gas, stirring dust, and igniting bursts of stellar birth. Observations show that the outer halo extends well beyond the visible stars. This halo is composed of extremely thin hot gas invisible to the human eye, but detected through X-ray observations and ultraviolet absorption. The halo does not stop abruptly, but rather fades gradually into intergalactic space, a reminder that galaxies are not sharply defined objects but diffuse systems whose edges blend into the greater universe. Within this halo lies a reservoir of matter that slowly rains inward, adding to the gas supply of the main body. The gravitational potential of the halo also acts as a shield, keeping stars and gas bound, even as tidal interactions with neighbors attempt to strip them away. From Earth, the galaxy appears small in the sky, yet its true scale is immense. Its disk spans tens of thousands of light-years, and its halo extends much further, reaching into the shared volume of the group. Across this scale, different processes take place simultaneously. On the outside, the halo records the impact of super winds that blow out of the core. These winds carry heavy elements forged in stellar interiors and spread them far into intergalactic space. The presence of these enriched winds shows that the galaxy does not evolve in isolation, but shares its products with the surrounding environment. Through such outflows, galaxies recycle matter and contribute to the chemical growth of the cosmos. When considering the outer regions, one must also imagine the faint traces of past interactions. Streams of stars and gas trail out from the main body formed when gravitational tides from nearby galaxies pulled material outward. Some of these streams are extremely diffuse, detectable only through deep imaging. They serve as fossil evidence of past encounters, revealing a history of motion and exchange. The outermost environment is shaped not only by its own activity, but also by these close interactions which alter the balance of gas supply and trigger waves of star formation inside. The radiation emerging from the central regions also plays a role in defining the outer environment. Intense bursts of ultraviolet light escape the disk and ionize gas in the halo. This forms glowing filaments that stretch outward, tracing the flow of matter and energy away from the galaxy. These filaments extend thousands of light years, creating patterns that resemble plumes rising from the surface of a fire. Observers using large telescopes can map these structures, finding that they are aligned with the axis of the galaxy, pointing away from the crowded starburst center. This symmetry suggests that the energy from stellar activity is funneled along preferred directions, shaping the outermost layers into visible forms. When viewed across multiple wavelengths, the outer regions display different faces. In visible light, dust lanes obscure the interior and give the galaxy its mottled look. In infrared light, streams of warm dust glow, outlining where the material has been heated by nearby stars. In X-ray and ultraviolet light, hot gas and energetic outflows dominate, painting a picture of violence hidden beneath the calm outer appearance. Each wavelength adds a new layer of understanding, showing how the outer regions are not static, but alive with the imprint of ongoing processes. Its place in the larger cosmic web also influences how it receives and loses matter. Gas flows inward along intergalactic filaments, providing raw material that can eventually reach the core. At the same time, the superwind from its center drives matter outward, producing a cycle of inflow and outflow. This constant exchange ensures that the outer regions remain in dynamic balance. Matter falls inward, fuels starburst activity, and is later expelled outward, enriching the surrounding space. In this way, the galaxy participates in the larger circulation of the universe, acting both as a consumer and a contributor of cosmic material. The image of this spindle of stars against the night sky hides the vast systems surrounding it. To the eye, it is simply a glowing spindle of light, but in truth it is enveloped in a halo that extends far beyond, fed by filaments, shaped by tides, and pierced by winds. It is a galaxy alive in its environment, not a solitary structure, but a node in the greater fabric of matter and energy. To begin a journey inward, one must first stand at this distance and appreciate the setting in which the Cigar Galaxy exists. This environment defines its past and continues to guide its present holding. Together, the materials that will soon be drawn into the more crowded and active zones of its disk. Within the local universe, this galaxy is a member of the M81 group, a small gathering of galaxies bound together by gravity. The group lies about 12 million light-years from Earth, and it contains several prominent systems, including the grand spiral known as Messier 81, and a number of smaller companions. These galaxies are not arranged at random, but are held together in a loose association, each one tugging upon the others across intergalactic space. The gravitational bonds are not strong enough to collapse the group into a single body, yet they are sufficient to keep the members in a slow and continuous dance. When astronomers map the motions of these systems, they find that orbits are not smooth circles, but are instead marked by tidal interactions and distortions. Such encounters have left faint signatures across the sky streams of stars and dust that arc outward from the main bodies. These features are best detected with deep imaging where faint bridges of matter reveal the quiet exchange between neighbours. The galaxy under focus is particularly influenced by its close interaction with Messier 81. Studies show that their paths brought them near one another in the past, and the gravitational forces stirred up the gas within, compressing it and sending waves of material toward the core. This disturbance is thought to have played a central role in the current burst of star formation. Unlike the calmer state of Messier 81, this system glows brightly in the infrared, a signal of intense activity hidden behind dust. The comparison between the two shows how environment can shape very different destinies for galaxies within the same group. One remains relatively serene, while the other burns with the light of new suns. The M81 group as a whole is an important laboratory for understanding galactic evolution. Its members are close enough for detailed study yet varied enough to display different stages of activity. Some are dwarfs, faint and irregular, while others are spirals with well-ordered arms. The galaxy that dominates this narrative is elongated and tilted, appearing cigar-shaped to observers, and stands out because of its unusually high rate of starbirth. This elevated activity is not random, but the direct result of gravitational interactions that funneled gas into its inner regions. In this way, the group setting provides both the resources and the disturbances that drive its behavior. Interactions within such groups are not rare in cosmic terms. Galaxies are social systems almost always found in associations rather than in isolation. When two systems pass close by, their gravitational fields distort one another, pulling out streams of gas and altering internal orbits. If gas is driven inward, star formation rises sharply, creating what astronomers call a starburst. Over time, the effects spread outward, enriching the environment with material cast off from newly formed stars and supernovae. The M81 group demonstrates this process vividly. Observations with radio telescopes reveal extended bridges of neutral hydrogen gas linking the major members. These bridges trace past encounters, preserving a memory of interactions long after the galaxies have moved on. The system we are examining is located at the intersection of these streams, indicating that it has both received and contributed material during such exchanges. Its outermost regions show signs of distortion, with arcs of stars pulled outward by tidal forces. These features are faint, yet they testify to the continuous give and take within the group. Within this environment, the galaxy does not simply exist as a passive participant, but actively shapes the group through its own outflows. The massive winds from its center drive hot gas outward into intergalactic space, spreading heavy elements that later seed new generations of stars in other systems. This exchange links the destinies of the group members together, ensuring that the chemical evolution of one influences the others. It is a reminder that galaxies are not closed boxes but nodes in a larger network of matter and energy. The group itself is moving within the broader structure of the universe, orbiting slowly within the gravitational pull of surrounding clusters. On this larger scale, its dynamics are shaped by the flow of dark matter, the unseen substance that outweighs visible stars and gas. The presence of dark matter defines the potential wells in which galaxies gather, and without it the group could not remain bound. Observations of orbital speeds within the galaxies, including the one described here, reveal that stars move too quickly to be held by visible mass alone. The extra gravity from dark matter halos ensures that the group remains intact over billions of years. This environment also influences the flow of gas as filaments of dark matter guide material into the group from the surrounding cosmic web. Such inflows maintain the gas reservoirs that allow starburst to continue. Without this steady supply, the galaxy would soon exhaust its fuel. Thus, the M81 group is both a source of disturbance and a provider of resources, setting the stage for the ongoing drama within its member. When viewed from afar, the group presents a variety of appearances across the spectrum. In visible light, the spiral arms of Messier 81 dominate, while the elongated structure nearby appears dusty and irregular. In radio light, the bridges of hydrogen emerge, showing the invisible ties between them. In infrared, the Starburst system shines brightest, its core radiating strongly as dust absorbs and re-emits the energy of young stars. This contrast highlights how each wavelength reveals a different aspect of the group. Together they show a portrait of galaxies bound not only by gravity, but also by the continuous flow of matter and radiation. The neighborhood of this elongated system is therefore far from quiet. It is a region where galaxies approach and retreat, where tides stretch and compress, and where gas streams are exchanged across vast distances. Every feature of the Starburst galaxy is shaped by this environment, from the halo that extends outward to the crowded clusters within its core. To understand the inner structure, one must first see it as part of this larger association. The M81 group provides the context, the supply, and the disturbance that together explain why the galaxy shines as it does today. As the narrative moves inward from the group as a whole, toward the outer halo and disk of this active system, the focus shifts from the wider environment to the structures that define the galaxy itself. In this way, the journey continues one step at a time from the cosmic neighborhood into the heart of the Cigar Galaxy. Surrounding the visible body of the galaxy lies a diffuse halo, an extended envelope that stretches far beyond the crowded disk of stars. This halo is not obvious in ordinary light, but its presence is revealed through careful observations in ultraviolet and X-ray wavelengths. The halo is made of thin hot gas and dark matter, both of which extend across a volume far larger than the luminous portion of the system. For astronomers, the halo represents the hidden mass that holds the galaxy together. Without it, the rapid rotation of stars and gas would fling material outward into intergalactic space. Instead, the halo provides the gravitational grip that binds the system into a coherent structure. The hot gas in this region is so rarefied that even across distances of thousands of light-years, particles rarely collide. Yet despite its thinness, the halo carries important clues about galactic evolution. Embedded within it are traces of heavy elements, oxygen, carbon, and iron that were forged in earlier generations of stars. These elements were expelled by stellar winds and supernova explosions, carried outward by the combined energy of many stars. Over millions of years, these products mixed with the tenuous halo, enriching it with the building blocks of future stars and planets. The halo also contains faint streams of material left behind by past encounters. Tidal interactions with neighboring galaxies pulled stars and gas outward, leaving behind arc-like structures that only deep imaging can reveal. These stellar streams orbit within the halo's silent witnesses to events that occurred hundreds of millions of years ago. They provide a fossil record of the gravitational history of the system, showing that it has not lived in isolation, but has been shaped continuously by its neighbors. Astronomers map these streams to reconstruct the encounters, much as an archaeologist reconstructs a site from fragments of stone and bone. The dark matter component of the halo cannot be seen directly, but its presence is inferred from the motion of stars. When astronomers measure the speed at which stars orbit within the galaxy, they find that the visible mass of stars and gas is insufficient to explain the rapid motion. An invisible mass must be present, extending far into the halo, adding the gravity needed to hold everything together. This dark matter outweighs the visible stars by several times, making it the dominant form of mass in the system. Without it, galaxies such as this one could not exist in stable form. The halo is not static but dynamic, constantly interacting with both the interior and the intergalactic medium. Streams of gas fall inward, guided by the gravitational pull of the dark matter. At the same time, powerful winds from the central starburst blow hot gas outward, enriching the halo and sometimes carrying it beyond the limits of the system. This balance of inflow and outflow ensures that the halo is a living part of the galaxy, not merely a background. It breathes with the rhythm of the system's inner activity, responding to changes in the core and distributing their effects across vast scales. Observations with X-ray telescopes reveal bubbles of hot gas rising into the halo. These bubbles are formed when clusters of massive stars release their energy into the surrounding medium. The result is a shock front that pushes gas outward, heating it to millions of degrees. These expanding shells extend thousands of light years into the halo, showing how local star formation can influence regions far beyond the disk. The fact that the halo is enriched with heavy elements confirms that these processes have operated for billions of years, each cycle adding new material to the cosmic reservoir. The shape of the halo is also influenced by magnetic fields. Though invisible, these fields thread through the galaxy and extend into the surrounding space. They align dust grains, guide charged particles, and shape the outflow of hot gas. Observations of polarized radio light reveal the structure of these fields, which often trace arcs that follow the contours of the halo. These patterns suggest that the halo is not merely a passive recipient of gas, but is organized by magnetic forces, which in turn influence how matter moves between the disk and the surrounding medium. At great distances from the central regions, the halo begins to fade into the intergalactic medium. There is no sharp boundary, only a gradual thinning of material until it becomes indistinguishable from the cosmic background. Yet even in these faint outskirts, the influence of the galaxy persists. Gas flows along filaments of dark matter toward the halo where it is captured and drawn inward. In this way, the halo acts as the gateway between the vast cosmic web and the concentrated activity within the system. Without this continuous supply, the inner regions would eventually run out of fuel for star formation. For astronomers, the halo is both a mystery and a necessity. It is difficult to study because its gas is faint and its dark matter is invisible. Yet its role is crucial, providing the framework within which the visible galaxy can exist. Every star in the disk, every cluster in the core, every stream of dust and gas is held by the unseen mass of the halo. Without it, the system would scatter into the void. When viewed as part of the larger M81 group, the halo plays an additional role. It buffers the galaxy from the full effects of tidal encounters, absorbing some of the gravitational stress and allowing the inner disk to remain coherent. At the same time, it records the scars of those encounters in the form of faint streams and shells. In this way, the halo is both shield and archive protector and historian. To the eye, the galaxy is a glowing spindle of light, but to the scientist it is a vast structure, embedded in an even larger envelope of unseen matter. This outer region defines the limits of the system and governs its evolution. As the journey continues inward from the halo to the streams of gas flowing outward and back, the influence of the unseen becomes the foundation upon which the visible rests. The Cigar Galaxy is therefore not only the bright spindle seen in telescopes, but also the vast halo that surrounds and sustains it. Emerging from the extended halo, the most striking outer structures are the immense filaments of gas that stream outward from the core, forming what astronomers call a galactic superwind. These are not thin, gentle wisps, but broad flows of ionized material that stretch for thousands of light years beyond the main disk. They are driven by the combined energy of millions of young stars and countless supernovae that detonate in the crowded central regions. When mapped through optical and X-ray observations, the filaments form a pair of opposing plumes that extend above and below the elongated body of the system. They carry with them the products of nuclear fusion carbon-oxygen and heavier elements that were forged in the interiors of massive stars. These outflows enrich the surrounding space, spreading essential elements far into intergalactic distances. The geometry of the superwind is shaped by the structure of the galaxy itself. Rather than expanding evenly in all directions, the gas escapes most easily along the axis that is perpendicular to the disk. The dense layers of dust and gas within the disk confine much of the energy, but the thinner regions above and below provide channels through which matter can flow. As a result, the outflow forms a bipolar shape rising like two vast chimneys into the halo. Observations show that these filaments glow with emission lines of hydrogen and oxygen signatures of ionization by the intense ultraviolet light of the central starburst. In X-rays, they shine with the heat of gas at millions of degrees Celsius, evidence of shock fronts created by overlapping supernova explosions. These combined features mark the superwind as one of the most energetic processes in the galaxy, a visible link between the inner star-forming core and the wider universe. The filaments are not smooth but clumpy and turbulent. Within them, pockets of denser gas resist the outward push, creating knots and arcs that glow brightly. Magnetic fields thread through these structures, guiding charged particles and adding complexity to the flows. At the edges of the filaments, cool gas mixes with the hot outflow, forming transitional zones where different phases of matter interact. These regions provide clues to how material is transferred from the galaxy into intergalactic space. The interaction between hot winds and cooler clouds shapes the eventual distribution of gas, some of which escapes entirely, while some falls back into the disk in a cycle of outflow and return. The scale of the superwind is immense. Each plume extends more than 10,000 light-years, a distance so great that it would take light itself tens of thousands of years to travel from one end to the other. Across this distance, the flow carries not only gas but also cosmic rays, high-energy particles accelerated by shocks within the outflow. These cosmic rays escape into intergalactic space, contributing to the background radiation that permeates the universe. Their presence demonstrates how processes within a single galaxy can influence environments far beyond their immediate borders. The energy budget of the superwind is staggering. Each massive star that ends in a supernova releases as much energy as the sun will emit in its entire lifetime. In the crowded starburst core, such explosions occur frequently, their shock waves overlapping and combining. The cumulative effect is a continuous push of gas outward. Radiation from massive young stars adds further pressure, while stellar winds contribute a steady stream of particles. Together, these mechanisms maintain the superwind over millions of years, ensuring that the outflow does not fade quickly, but persists as long as star formation remains intense. For astronomers, these filaments provide a unique opportunity to study feedback processes on galactic scales. They show how star formation, while creating new generations of stars, also regulates itself by expelling gas. If too much gas is blown away, star formation slows, preventing the system from consuming all its resources at once. This feedback ensures that the galaxy's evolution is balanced, with bursts of activity followed by quieter periods. The filaments therefore represent both the vigor of the current starburst and the seeds of future regulation. Observations across wavelengths reveal different aspects of the outflow. In visible light, glowing filaments trace the paths of ionized gas. In infrared, warm dust within the outflow shines faintly carried outward along with the gas. In X-rays, hot plasma fills the cavities between the filaments, outlining the regions where energy is most intense. Radio observations detect synchrotron emission from electrons spiraling along magnetic fields, highlighting the role of magnetism in shaping the flows. Each wavelength adds a new layer of understanding, building a picture of the superwind as a complex and dynamic system. The influence of the superwind extends into the halo, where it interacts with the diffuse hot gas that already surrounds the galaxy. This interaction creates shock fronts and turbulence that stir the halo, mixing newly enriched material with older gas. Over time, this mixture will either escape into intergalactic space or rain back down onto the disk, providing fresh fuel for future star formation. In this way, the superwind is both an engine of enrichment and a recycler of material. It demonstrates that galaxies are not isolated containers, but participants in the continuous circulation of matter through the cosmos. For nearby galaxies in the M81 group, the outflows may even provide additional material. Gas escaping from the Starburst system can drift into the intergalactic medium, where gravitational interactions redistribute it among neighbours. In this sense, the superwind is a mechanism for sharing resources within the group, linking the chemical evolution of multiple galaxies together. The presence of these vast plumes therefore carries implications not only for the system itself, but also for the environment in which it resides. To the human eye through a telescope, the galaxy appears as a narrow spindle of light, yet hidden within it are engines of extraordinary power. The filaments of the superwind are invisible without specialized instruments, but when revealed they show the true scale of activity within the system. They testify to the energy released by countless stars, each one a tiny source contributing to a collective force that reshapes the surrounding universe. These structures are among the most dramatic features of the galaxy, carrying its influence far beyond the limits of its disk. As the exploration moves inward from these filaments, the next step is to encounter the dust-laden outer disk, where the interplay of obscuring material and starlight begins to define the visible face of the Cigar Galaxy. From the wide plumes of the superwind, attention turns to the outer disk of the galaxy, where thick lanes of dust define much of its visible appearance. To observers on Earth, the system presents itself as an elongated spindle, darkened and mottled by threads of obscuring material. These dust lanes stretch across the disk, cutting into the light of billions of stars and giving the galaxy its characteristic smoky look. Dust, though only a tiny fraction of the total mass, plays an outsized role in shaping the visible face of a galaxy. Each grain is smaller than a particle of smoke composed primarily of carbon, silicon, and oxygen compounds. Yet in immense numbers, these grains absorb and scatter light, concealing the inner regions and re-radiating energy in the infrared. The result is a galaxy that glows brilliantly at longer wavelengths, even as it appears darkened in visible light. Within the outer disk, the dust is not evenly distributed. It gathers into dense lanes that wind through the stellar population, often following the gravitational patterns imposed by the inner bar. These lanes trace regions where gas and dust are compressed, forming the sites of future star formation. The interplay of dark lanes and bright starlight creates a complex pattern, one that reveals the underlying structure of the disk. Observations with infrared telescopes pierce through the obscuring dust, revealing the crowded regions hidden behind. These views show that the disk is packed with gas clouds and young stars, each one contributing to the overall activity of the galaxy. The outer disk is also the site of older stellar population stars that have lived for billions of years and now form a quiet background. These stars contribute most of the visible light in the outer regions, giving the disk a soft, diffuse glow. Their presence contrasts with the central starburst where young stars dominate. This mix of old and new populations is typical of disk galaxies, but in this case the contrast is sharper because of the intense activity in the core. The outer disk therefore serves as a bridge between the calm outskirts and the crowded centre, a region where past and present coexist. The dust within the disk also acts as a tracer of galactic dynamics. Its patterns reveal how gas flows through the system, funneled inward by the gravitational pull of the central bar. As gas moves along these lanes, it collides and compresses cooling enough to form molecular hydrogen clouds. These clouds in turn provide the raw material for the birth of new stars. The outer disk is therefore not merely a static structure, but an active participant in the cycle of star formation, channeling material inward and shaping the future of the galaxy. When observed in radio wavelengths, the outer disk reveals even more detail. Neutral hydrogen gas extends beyond the visible limits, forming a broad disk that rotates with the stars. This gas acts as a reservoir feeding the inner regions as gravitational forces drive it inward. The distribution of hydrogen also shows signs of past interactions. Tidal forces from nearby galaxies have distorted the outer gas, creating asymmetries and warps that betray the influence of neighbours. These features demonstrate how the outer disk is continually reshaped by both internal processes and external encounters. Within the dust-rich outer regions, star clusters also appear. Some of these clusters are ancient globulars, tightly bound groups of stars that formed in the early history of the galaxy. Others are younger open clusters, more loosely bound and destined to disperse over time. Their presence provides evidence of continuous star formation across billions of years. The contrast between old clusters and new clusters underscores the layered history of the disk, where cycles of formation and dispersal have played out repeatedly. The interplay of dust gas and stars in the outer disk creates a complex environment. Dust absorbs starlight and warms re-emitting energy in the infrared. Gas cools and collapses, forming dense molecular clouds. Stars form within these clouds, ignite nuclear fusion, and begin to shine, releasing radiation that alters the surrounding gas. Over time, massive stars explode as supernovae, enriching the disk with heavy elements and stirring the gas into new patterns. Each of these processes leaves its mark, and together they define the character of the outer disk. From Earth, the dusty outer disk is one of the most recognizable features of the galaxy. Its mottled appearance gives the spindle its distinct look, making it stand out even in small telescopes. Yet beneath that obscuring dust lies a world of activity hidden from view in visible light, but revealed in infrared and radio. To understand this region is to see how the visible face of the galaxy is shaped by unseen forces, and how the interplay of dust and gas governs the balance between concealment and revelation. The dust also influences how the galaxy appears across cosmic distances. Distant observers in other galaxies would see it as a heavily reddened system, glowing strongly in the infrared but dimmed in the optical. This property has implications for how astronomers interpret the light from more remote galaxies, where dust can conceal much of the underlying structure. By studying a nearby example, scientists learn how to correct for these effects in more distant systems. The outer disk is therefore both a subject of direct interest and a tool for broader understanding. The outermost stars of the disk also blend gradually into the halo, creating a transition between the dense stellar body and the diffuse environment beyond. Here stars are fewer, and the density of gas and dust drops. Yet even in these outskirts, traces of dust remain, faintly obscuring the light of background stars and revealing the presence of material far beyond the visible limits. These faint features remind us that the disk does not end abruptly but tapers off into the surrounding medium. As the narrative continues inward, the focus shifts from the obscuring dust of the outer disk to the stars that lie within it. Their light, shaped by dust and gas, offers the next layer of detail in the story of this system. In this way, the path proceeds gradually from the outermost obscuring structures toward the inner bar and eventually the luminous core of the Cigar Galaxy. Deeper within the dusty outer disk, the distribution of stars begins to change, revealing the blend of older populations and scattered younger groups. The outskirts of the system are dominated by stars that formed many billions of years ago. These ancient suns are generally cooler, redder, and less massive, and they shine with a steadier light than the vigorous blue stars of younger ages. Together they form the diffuse background that gives the outer disk its gentle glow. Their orbits are slightly more random than those of the stars closer to the bar, creating a smoother pattern of light. They act as a fossil record of the galaxy's earliest epochs, preserving the conditions under which the first stellar generations formed. Among this field of aged stars lie patches of younger activity. Star formation has not been limited only to the core. Even in the outer disk, regions of compressed gas have given rise to new clusters. These scattered pockets shine more brightly than the older stars around them, their blue light cutting through the dusty lanes. Each of these clusters represents a more recent burst of activity, often triggered by density waves passing through the disk, or by tidal disturbances from encounters with nearby galaxies. Though smaller in scale than the central starburst, they demonstrate that the process of starbirth is widespread. Observations reveal that the mix of stars in the outer disk provides insight into the chemical history of the system. Older stars contain fewer heavy elements, having formed when the universe was younger and less enriched by stellar processes. Younger stars, on the other hand, show higher proportions of oxygen, carbon, and iron, evidence of the recycling of matter through successive generations. This gradient of metallicity from older to younger populations allows astronomers to trace the gradual enrichment of the galaxy, showing how it has evolved chemically over billions of years. The distribution of stellar populations also shows the influence of dynamics. The outer disk is not a perfect circle, but somewhat warped, shaped by gravitational interactions. This distortion alters the orbits of stars and gas, causing certain regions to compress, while others stretch outward. Where gas is compressed, stars form more readily, leading to the uneven pattern of younger clusters seen today. The warp itself is thought to be the result of tidal encounters with neighbouring galaxies in the M81 group. Such warps are common in disk galaxies, and they provide clues about past interactions and the current gravitational environment. Within this outer disk, globular clusters are also present. These dense spherical groups contain hundreds of thousands of stars, many of which are as old as the galaxy itself. Globular clusters orbit in the outer regions, tracing wide paths that carry them through both the disk and the halo. Their stability over billions of years makes them valuable markers of galactic history. By studying their motions, astronomers can infer the distribution of mass in the galaxy, including the unseen dark matter that extends far into the halo. These globulars act like ancient witnesses, moving slowly around the spindle of stars while retaining the memory of the galaxy's earliest formation. The interplay of old stars, young clusters, and dense globulars creates a layered portrait of the outer disk. Each type of population contributes to the overall light, but in different ways. The older stars form the dim backdrop, the younger clusters provide bright points of contrast, and the globular clusters stand as dense, luminous knots. Together they reveal that the outer disk is not uniform, but is instead a mosaic of stellar ages and histories. The gas that remains in the outer disk plays an important role in sustaining future star formation. Neutral hydrogen extends beyond the visible stars, forming a diffuse reservoir that slowly drifts inward. Where this gas is compressed either by gravitational forces or by density waves, it forms molecular hydrogen, which in turn collapses into stars. Thus, even in regions dominated by older populations, the potential for new stars persists. The outer disk is therefore a place of continuity where ancient light and new birth coexist. Dust also influences how the stellar populations are seen. By absorbing and scattering visible light, it dims the appearance of stars, especially the younger, bluer ones. Yet in the infrared, these same regions glow more strongly as dust grains warmed by starlight emit their energy at longer wavelengths. Observations in infrared allow astronomers to peer through the dust and measure the true number and distribution of stars. These studies confirm that the outer disk holds both old and new populations layered together in a complex structure. The chemical enrichment of the outer disk provides further evidence of its long history. Spectroscopic studies of its stars show varying levels of elements such as iron and magnesium, with older stars containing less and younger stars containing more. This enrichment results from the continual cycle of birth and death as stars forge heavy elements in their cores and release them through winds and supernovae. Over time, this material mixes with gas and becomes part of new generations. The outer disk is therefore not only a place where stars reside, but also a record of the gradual transformation of matter across cosmic time. In the larger context of the galaxy, the outer disk serves as a transitional zone between the quiet halo and the crowded central regions. It shows how material flows inward, guided by gravity, while at the same time it records the scars of past interactions. Its stars reveal both the beginnings of the galaxy and the ongoing processes that sustain it. To the observer, it may appear as a faintly glowing edge darkened by dust and mottled with patches of light. But beneath this simple appearance lies a complex history written in starlight. As the path continues inward, the focus shifts from the stellar populations of the outer disk to the invisible structures that shape them. Magnetic fields thread through the system, aligning dust-guiding gas and influencing the very patterns of star formation. The next step in the journey is to examine how these unseen forces contribute to the organization and evolution of the Cigar Galaxy. Threaded through the gas and dust of the galaxy are magnetic fields invisible yet influential in shaping how matter is arranged and how it moves. These fields do not glow with their own light, yet their presence can be detected through the alignment of dust grains and the behavior of charged particles spiraling along magnetic lines. Observations in polarized radiolight reveal patterns across the disk and extending into the halo, showing that magnetism is not confined to the central regions but reaches far outward. The strength of these fields is modest when compared with the forces of gravity, yet over large scales they play a crucial role in guiding gas-shaping clouds and influencing the direction of galactic winds. In the outer disk, magnetic fields are aligned along the dust lanes, tracing the paths where gas flows inward toward the core. These alignments suggest that the fields help organize the movement of matter, preventing turbulence from scattering gas too widely and allowing it to compress into the dense clouds where stars can form. Without this guidance, the gas might disperse too easily, reducing the efficiency of star formation. Instead, the fields provide a kind of scaffolding, invisible yet effective, around which matter gathers. Within the halo, the fields extend into the large filaments of the superwind, threading through the hot outflows and adding structure to their shapes. Charged particles accelerated by supernova explosions spiral along these lines, producing synchrotron radiation detectable at radio wavelengths. The resulting patterns of polarized light reveal arcs and loops that follow the flow of the wind, confirming that magnetism plays a role in shaping how gas escapes into intergalactic space. These patterns are not random but coherent across thousands of light years, showing that the fields are ordered on galactic scales. The origin of such large-scale magnetic fields is a subject of continuing research. They are thought to arise through dynamo processes, in which the motion of conducting gas within the disk generates and amplifies magnetic fields over billions of years. Rotation of the galaxy combined with turbulence in the interstellar medium creates a self-sustaining cycle that maintains the fields. The result is a system where magnetism is woven into the very fabric of the galaxy, influencing matter at every scale. In the central regions where star formation is intense, the magnetic fields are stronger and more tangled. Here, stellar winds, radiation, and supernovae stir the gas, violently twisting and amplifying the fields. This turbulence adds complexity, but the overall effect remains. The fields continue to guide gas flows, channeling them along certain paths and resisting collapse along others. The presence of these stronger fields near the core helps explain why the superwind emerges in structured filaments rather than as a uniform outflow. Magnetism shapes the direction of escape, giving the wind its observed geometry. For the outer disk, the magnetic fields act more gently. They align dust grains so that their long axes are oriented consistently. This alignment produces polarization of starlight passing through, allowing astronomers to map the fields indirectly. Such studies show that the fields are coherent over wide regions, suggesting that they are not easily disrupted by local events. Instead, they persist as long-term features influencing the movement of gas clouds across the disk. By comparing these patterns with the distribution of star-forming regions, astronomers find that fields often run parallel to spiral structures, supporting the idea that magnetism plays a role in maintaining the order of the disk. The influence of magnetic fields also extends to the small scale of star formation. Within molecular clouds, the fields resist gravitational collapse, slowing the rate at which gas condenses into stars. This regulation prevents clouds from fragmenting too quickly and allows star formation to proceed in a more balanced way. When collapse does occur, the fields guide the flow of gas into the forming star, shaping the accretion process. In this sense, magnetism acts as both regulator and organizer, ensuring that star formation proceeds steadily rather than chaotically. Magnetic fields also interact with cosmic rays, the high-energy particles that pervade the galaxy. These particles travel along field lines, influencing the heating and ionization of gas. By tracing the paths of cosmic rays, astronomers can gain further insight into the structure of the fields themselves. The interplay between magnetism and cosmic rays is particularly evident in the superwind, where the accelerated particles follow magnetic arcs far into the halo, carrying energy outward and contributing to the enrichment of intergalactic space. Observations of the Cigar Galaxy have become a cornerstone in the study of galactic magnetism because of the clarity with which these features are displayed. The combination of intense star formation, strong winds, and clear alignment of dust provides a laboratory for understanding how magnetic fields operate on both small and large scales. By comparing this system to calmer galaxies, scientists can measure how magnetism responds to different environments. The results show that while gravity drives the overall structure, magnetism adds an important layer of organization that cannot be ignored. In visible light, the influence of magnetism is hidden, but in radio polarization, the patterns emerge vividly. These patterns reveal a galaxy not only composed of stars and gas, but also threaded by invisible lines of force. They show that the evolution of the system cannot be understood without considering the role of magnetic energy. Over billions of years, this energy has shaped the way gas flows, how stars form, and how winds escape. It is a quiet influence, not as obvious as the bright light of stars or the dark shadows of dust, but its effects are profound. The presence of magnetic fields also has implications for the long-term evolution of the system. By regulating gas flows, they influence how quickly the galaxy consumes its fuel. By guiding winds, they determine how much matter escapes into intergalactic space. By interacting with cosmic rays, they affect the heating of the interstellar medium. Each of these roles contributes to the overall balance of processes that define the galaxy's character. As the journey inward continues, the magnetic scaffolding gives way to the denser structures of the bar and inner disk. Here, gravity dominates more strongly, drawing gas toward the crowded core. Yet even in these inner regions, the unseen hand of magnetism continues to shape the flow, ensuring that the processes of star formation and feedback remain ordered. With this understanding, the path now turns toward the bar and inner disk, where the concentration of stars becomes greater and the structures more defined, leading the way toward the crowded heart of the Cigar Galaxy. Moving inward from the outer disk, the structure of the galaxy changes as stars and gas become more densely arranged within the central bar and inner disk. This region is defined by a bright elongated feature that cuts across the galaxy's core guiding material along its length and feeding the processes at the center. The bar is not a separate structure but an arrangement of stars and gas shaped by gravitational instabilities. Over billions of years, slight asymmetries in the disk grew until they formed a stable elongated pattern, with stars orbiting in paths that reinforce the bar's shape. Gas responds to these gravitational patterns as well, flowing inward along the bar and accumulating near the core. This steady transport of material is one of the key mechanisms that fuel the starburst activity at the center. The bar itself shines with the light of countless stars, most of them older and more evolved. These stars orbit in elongated paths that give the bar its shape, their combined light forming a bright band when seen from Earth. Intermixed with them are pockets of younger stars formed where gas has been compressed along the bar's length. These younger populations appear bluer and brighter, standing out against the golden glow of older stars. The inner disk around the bar contains a mixture of stellar populations as well. Here the density of stars is much higher than in the outskirts, creating a more crowded field. The inner disk rotates more rapidly, with stars and gas completing orbits in shorter timescales. This rapid motion enhances the mixing of material, blending older and younger populations and creating a dynamic environment. Dust is also present, tracing lanes that cut into the bar and inner disk. These dust lanes are often aligned with the flow of gas, marking the paths where material streams inward. In visible light, the dust appears as dark streaks, while in infrared it glows as it absorbs and re-emits the energy of surrounding stars. Observations show that these lanes are particularly prominent near the ends of the bar where gas is funneled into the inner regions. The result is a continuous supply of fresh material to the core, sustaining the high rate of star formation. The bar also influences the dynamics of the entire galaxy. By redistributing angular momentum, it allows gas to move inward more efficiently than it would in a purely circular disk. This process changes the balance of material between the outer and inner regions, concentrating resources in the center and enhancing the starburst. At the same time, the bar helps to stabilize the outer disk by transferring energy outward. In this way, it acts as a bridge between the calm outskirts and the crowded core, shaping the flow of matter and energy across the system. Within the inner disk, stellar density increases dramatically. Stars are packed more closely, and their combined light gives the region a luminous appearance, even when viewed through the obscuring dust. Many of these stars are older, long-lived populations that contribute to the bulk of the light. Yet mixed among them are younger clusters formed more recently from gas compressed along the bar and funneled into the center. These clusters add brightness and variety, their blue light contrasting with the reddish glow of older populations. The dynamics of the inner disk are complex. Stars follow nearly circular paths, but gas flows are influenced strongly by the gravitational pull of the bar. This causes shocks and compressions along the dust lanes, triggering the collapse of gas clouds into new stars. As a result, star formation in the inner disk is enhanced compared with the outer regions, though it is still overshadowed by the extraordinary activity in the central starburst zone. Observations in multiple wavelengths reveal the intricate interplay of stars, gas and dust in the bar and inner disk. In visible light, the dense star fields shine through the dust, creating a mottled appearance. In infrared, the dust lanes glow, outlining the paths of gas flows. In radio, the distribution of hydrogen is mapped, showing how gas is guided inward along the bar. In X-rays, hot gas heated by supernova is visible, marking regions of intense stellar feedback. Together, these views create a comprehensive picture of the inner structures, showing how they function as a system of transport and transformation. The bar also affects the shape of the inner disk by creating resonances regions where the orbital periods of stars and gas align in special ways with the rotation of the bar. These resonances can concentrate gas into rings or trigger waves of star formation. In some galaxies, prominent inner rings are seen, though in this case the features are more subtle. Still, the influence of resonances adds another layer of organization to the inner disk, ensuring that matter is not randomly distributed, but arranged in patterns guided by gravity. For astronomers, the bar and inner disk are crucial to understanding how starburst galaxies operate. They show how material is funneled from large scales to small, feeding the central core with a continuous supply of gas. Without the bar, the inflow would be less efficient and the starburst might fade more quickly. With the bar, the flow is sustained, allowing the central regions to maintain their extraordinary pace of star formation. The inner disk also acts as a buffer, absorbing some of the energy released by the core. Stellar winds, radiation and supernovae push outward, but the dense population of stars and gas in the inner disk helps to absorb and redistribute this energy. This balance ensures that the system remains stable even under the intense pressures of the starburst. To the observer, the bar and inner disk appear as the glowing heart of the spindle, brighter and denser than the regions outside. Yet beneath this simple appearance lies a complex interplay of dynamics, flows and feedback. Every star, every cluster, every dust lane is part of a larger system that channels matter inward and regulates the galaxy's evolution. The next step in the journey moves further inward from the bar and inner disk to the crowded central starburst zone, where the pace of star formation rises to extraordinary levels and the core of the Cigar Galaxy burns with the light of thousands of suns. At the very heart of the galaxy lies the starburst zone, a region where the rate of star formation is hundreds of times greater than that of calmer spirals such as the Milky Way. Here, dense concentrations of gas and dust collapse into clusters of new stars at an extraordinary pace, filling the central few thousand light-years with radiant energy and powerful feedback. The core glows intensely in infrared, the dust absorbing ultraviolet and visible light from newborn stars and re-emitting it as heat. This hidden brightness is one of the defining characteristics of a starburst galaxy, and it reveals how much activity is occurring behind the obscuring veils of dust. In this region, the density of stars is extreme. Massive clusters pack thousands of suns into volumes only a few dozen light-years across, creating some of the most crowded stellar neighborhoods known. Many of the stars formed here are massive, burning brightly, and living only a few million years before exploding as supernovae. Their short lives mean that the starburst zone is in constant motion, with new stars forming as others quickly die. This cycle drives the turbulence and energy that define the region. The gas in the core is compressed into giant molecular clouds, each one containing enough material to form thousands of stars. Under the influence of gravity, these clouds fragment into smaller clumps, collapsing until nuclear fusion ignites. The result is a continuous wave of starbirth with clusters emerging one after another. Observations show that the total rate of star formation in this system is several solar masses per year, a pace much higher than the slow and steady rhythm of galaxies like our own. This extraordinary activity is sustained by the inflow of gas along the bar and inner disk. Without a steady supply, the gas in the core would be consumed quickly, and the starburst would fade. Instead, the bar channels material inward, ensuring that the central regions remain fueled. This balance between supply and consumption defines the current state of the galaxy, locking it in a phase of heightened activity that may last tens of millions of years. Within the starburst zone, conditions are extreme. Radiation fields are intense, heating nearby dust and gas to high temperatures. Stellar winds from young stars push against surrounding material, carving cavities and driving shock waves. Supernova explosions add to the turmoil, releasing vast amounts of energy and enriching the gas with heavy elements. These combined processes stir the core into a turbulent state where clouds of gas collapse, fragment, and are blown apart in rapid succession. This turbulence does not prevent star formation. Rather, it helps regulate it, shaping the distribution of clusters and ensuring that the activity is spread across the core. The density of young clusters makes the central region one of the most luminous in the local universe. Infrared observations show knots of brightness corresponding to massive clusters only a few million years old. These clusters are bright enough to outshine entire dwarf galaxies, even though they occupy only tiny portions of the core. Each cluster contains stars of all sizes, from massive blue giants to smaller long-lived stars like the Sun. Over time, the massive stars will die while the smaller stars will persist, leaving behind a record of the starburst in the form of dense stellar groupings. The chemical composition of the core is also distinctive. The presence of heavy elements indicates that many generations of stars have already lived and died here, enriching the gas with the products of fusion. This enrichment influences how new stars form, altering their lifetimes and the types of planets that might one day develop around them. The starburst core is therefore not only a site of rapid star formation, but also a crucible of chemical evolution, where the raw material of future systems is being prepared. The scale of energy released in the core is difficult to grasp. Each massive star emits thousands of times more light than the Sun, and when multiplied across thousands of such stars, the total luminosity is staggering. Added to this are the energies of supernovae, each explosion releasing as much energy as the Sun will emit in its lifetime. Together, these processes generate the winds that drive the superwind out of the galaxy, linking the activity of the core to the structures far beyond the disk. For astronomers, the starburst zone is both a challenge and a gift. Its extreme conditions push the limits of models of star formation, yet its relative proximity makes it possible to study details that are inaccessible in more distant starburst galaxies. Observations across the spectrum provide insights into how stars form in crowded environments, how feedback regulates activity, and how entire galaxies evolve during such phases. The lessons learned here can be applied to understanding galaxies in the early universe, when starburst activity was more common. The central starburst is not a permanent feature. Over tens of millions of years, the supply of gas will diminish, either consumed in star formation or expelled by winds. When that happens, the rate of star formation will fall, and the galaxy will settle into a quieter state. For now, however, the core blazes with activity, providing one of the most vivid examples of how galaxies can transform their energy into new generations of stars. To the human eye, the core of the galaxy is hidden by dust appearing only as a brightened centre within the spindle of light. Yet behind that obscuration lies a world of extraordinary brightness, turbulence, and creation. It is a region where the processes of star formation operate at their most intense, shaping the evolution of the galaxy and influencing its surroundings for millions of light years. This inner starburst zone represents the climax of the inward journey, the place where the flows of gas and the forces of gravity converge to ignite a furnace of creation. As the exploration continues, the focus turns to the molecular gas clouds. Within this core, the very birthplaces of the stars themselves, where cold matter condenses into the seeds of new suns in the heart of the Cigar Galaxy. At the foundation of the starburst core lie vast molecular gas reservoirs, immense clouds of cold hydrogen that serve as the raw material for star formation. These clouds are colder than the surrounding medium, often only a few tens of degrees above absolute zero, and their low temperatures allow hydrogen atoms to bond into molecules. Within these molecular clouds, dust grains provide surfaces where additional molecules can form, including carbon monoxide and water. Such compounds, though present in tiny fractions compared to hydrogen, are crucial markers that astronomers use to trace the distribution of the gas. Observations in millimeter and submillimeter wavelengths reveal that the central regions of the galaxy are packed with these reservoirs far denser and more abundant than those in the quieter spirals of the local universe. The molecular gas does not lie evenly across the core, but is concentrated in giant complexes, each one stretching across hundreds of light years and containing millions of solar masses of material. These complexes are turbulent, stirred by the gravity of the bar and the energy of nearby young stars. Within them, dense knots form where the gas collapses further under its own weight. These knots are the cradles of star clusters, the places where gravity wins over turbulence and ignites the nuclear furnaces of new suns. The balance between collapse and disruption defines the rate of star formation. Too much turbulence and the gas is scattered, too little and it collapses all at once. In this starburst system, the balance is tipped toward rapid collapse sustained by the constant inflow of new gas along the bar. This inflow ensures that molecular reservoirs are replenished even as they are consumed. The molecular clouds also act as shields, protecting their interiors from the harsh radiation of nearby young stars. Dust within the clouds absorbs ultraviolet light, creating dark, cool regions where gas can remain molecular. These sheltered zones allow collapse to proceed hidden from view in visible light, but detectable through radio and infrared observations. In the densest regions, the gas fragments into clumps that form entire clusters of stars rather than single suns. The efficiency of this process is much higher than in calmer environments, which is why the core can sustain its remarkable starburst rate. Observations show that many of the clusters forming in these clouds are massive, containing thousands of stars. Such clusters are born bound together by their own gravity, and many will survive for billions of years as globular-like systems. Others will disperse over time, their stars merging into the general population of the disk. Either way, the formation of such dense clusters is a hallmark of the intense conditions within molecular reservoirs of a starburst galaxy. The chemical composition of the molecular gas provides additional insight. Traces of carbon monoxide, ammonia, and formaldehyde reveal the complex chemistry occurring on dust grain surfaces. These molecules do not influence the overall dynamics, but they serve as valuable traces of temperature, density, and pressure within the clouds. They show that conditions vary widely from one cloud to another, with some regions remaining cool and quiescent, while others are heated by nearby star formation. This patchwork of environments highlights the complexity of the starburst core, where many stages of starbirth and destruction occur side by side. The inflow of gas from the bar ensures that these molecular reservoirs are continuously resupplied. Without such inflows, the intense star formation would deplete the gas in only a few tens of millions of years. Instead, the molecular content remains abundant, allowing the starburst to persist. Radio maps of carbon monoxide show streams of gas entering the core, spiraling inward and feeding the central complexes. This process demonstrates how the large-scale structure of the galaxy directly sustains the smallest scales of starbirth. Feedback from newly formed stars also shapes the fate of these reservoirs. Stellar winds, radiation and supernovae inject energy into the clouds, compressing some regions while dispersing others. This feedback creates a cycle star formation, both consumes gas and triggers more collapse in nearby regions. In this way, the process is self-sustaining as long as fresh gas continues to arrive. The result is a constantly shifting landscape of molecular clouds, some being destroyed, others forming all within the crowded central environment. The scale of these reservoirs is striking. Some of the largest contain enough mass to form entire dwarf galaxies, yet within this system they exist only as components of the central starburst. Their presence highlights the extraordinary concentration of material in the core, a concentration made possible by the gravitational funneling of the bar and inner disk. This mass of gas represents both the present activity and the future potential of the galaxy, since it will determine how long the starburst can continue. The role of molecular reservoirs in galactic evolution extends beyond the current starburst. As clusters form and stars evolve, the enriched material they release will mix back into the molecular gas, altering its composition. Each cycle adds new heavy elements, increasing the metallicity of future stars. This process of chemical evolution is one of the key ways galaxies change over cosmic time, and the molecular reservoirs at the heart of the starburst are the sites where it is most intense. For astronomers, studying these clouds in detail is a challenge. They're hidden behind thick dust and can only be traced through radio and infrared light. Yet these observations are critical because they reveal the actual fuel of star formation. Without understanding the molecular reservoirs, the story of the starburst would be incomplete. By mapping them, astronomers can see how gas flows inward, how it collects into complexes, and how it is transformed into stars. The reservoirs also provide a connection between the inner and outer scales of the galaxy. They are fed by inflows from tens of thousands of light years away, yet they operate on scales of only hundreds of light years. They demonstrate how processes across many orders of magnitude are linked from the rotation of the entire disk down to the collapse of individual star-forming cores. This nested hierarchy of scales is one of the defining features of galactic evolution. To the eye, the molecular reservoirs are invisible, hidden within the dusty core. Yet they are the true engines of the starburst, the factories where stars are assembled from cold gas. They represent the deepest layer of the journey inward from the outer halo through the superwind, the dust lanes, the stellar populations, the bar, and finally into the raw material of creation. From here, the next step leads to the newborn stellar clusters themselves, where the results of this process shine with youthful brilliance in the heart of the Cigar Galaxy. Within the molecular reservoirs of the core star formation proceeds at a remarkable pace, producing dense clusters of newborn stars. These clusters are the direct outcome of the collapse of gas within giant molecular clouds, and they represent some of the most crowded stellar environments known. Each cluster contains thousands of stars packed within a relatively small volume, making them far denser than the regions of the Milky Way where the Sun resides. The light from these young stars is intense, particularly from the massive blue giants that dominate the early stages of the clusters. Their combined output is sufficient to light up the surrounding dust and gas, creating bright knots, visible in infrared and optical observations. The clusters form in rapid succession one after another as inflowing gas is compressed into new clouds. Some of the youngest clusters are only a few million years old, still embedded in the remnants of the clouds that birthed them. These clouds glow as the ultraviolet radiation from the newborn stars ionizes the surrounding hydrogen, producing luminous regions of energized gas. The contrast between the dark dust lanes and the glowing clouds gives the core its mottled appearance in images, while in the infrared the hidden brilliance of the clusters shines through. The most massive clusters rival globular clusters in size and density, although they are far younger. Over time, some of these will survive as long-lived bound systems, while others will disperse as their stars drift apart under the influence of galactic tides. The presence of such massive young clusters is a defining feature of starburst galaxies, and their study provides insight into how globular clusters might have formed in the early universe. The stars within these clusters cover a full range of masses, from small red dwarfs that will persist for trillions of years to short-lived giants that will explode within only a few million years. The mix of stars determines the future evolution of the clusters as the giants enrich their environment, while the smaller stars provide the long-term light. The intense radiation from massive stars has a profound effect on their surroundings. It heats and ionizes nearby gas, driving it outward and creating bubbles and cavities. Stellar winds add to this process, blowing material away and exposing the young cluster more fully. These feedback effects can trigger further star formation in nearby regions by compressing surrounding gas, but they also limit the growth of the cluster itself by dispersing the remaining molecular material. The result is a dynamic balance between birth and disruption, a process that ensures the starburst is not uniform but instead patchy, with clusters scattered throughout the core. Supernovae soon follow as the most massive stars reach the end of their short lives. These explosions inject enormous amounts of energy into the surrounding medium, stirring turbulence and enriching the gas with heavy elements. The newly formed clusters therefore become both creators and destroyers, adding new stars to the galaxy while simultaneously reshaping their environment. The feedback from these clusters is one of the primary drivers of the galactic superwind, linking the small scale of starbirth to the large scale of gas outflows that extend thousands of light years. The chemical enrichment produced by the clusters is significant. Heavy elements forged in the cores of massive stars are spread into the surrounding gas, altering its composition and preparing it for future generations of stars. This enrichment is evident in the spectra of the core, where strong lines of oxygen, carbon and nitrogen reveal the presence of freshly produced elements. Over time, this process will increase the metallicity of the galaxy, changing the characteristics of stars that form in later epochs. Observations of these young clusters also provide a unique opportunity to study star formation under extreme conditions. Unlike the relatively sparse environments of the Milky Way's spiral arms, the clusters here form in highly crowded regions where interactions between stars are frequent. These interactions can alter the paths of stars, ejecting some into the field while binding others more tightly into the cluster. The crowded conditions may also influence the formation of planetary systems, as close encounters can disrupt the disks of gas and dust around young stars. In this way, the environment of the starburst core shapes not only the stars themselves, but also the potential for planets and other structures that might arise around them. The sheer luminosity of the clusters makes them visible across great distances. In infrared surveys, the core glows brightly because of the combined light of these young stars heating the dust. In radio observations, the ionized gas around them produces strong emission lines. These multiple wavelengths allow astronomers to trace the life cycle of the clusters from their emergence in dense clouds to their dispersal into the general stellar population. Each cluster represents a snapshot of this process, and together they reveal the rhythm of starburst activity. The number of clusters forming in the core is remarkable. At any given time, dozens of massive clusters may be in various stages of development, each one contributing to the overall brightness of the galaxy. This abundance is a direct result of the continuous inflow of gas from the bar and inner disk, which ensures that new clouds are always available to collapse. Without this inflow, the activity would decline rapidly, but with it the starburst can persist for tens of millions of years. The legacy of these clusters will endure long after the starburst fades. The smaller stars will continue to shine for billions of years, adding to the background population of the galaxy. The most massive clusters that remain bound will survive as dense stellar systems orbiting the core as ancient witnesses of this period of intense creation. In this way, the clusters serve as both the products and the record of the starburst, preserving its history in their light. To the observer, the core may appear as a glowing blur through the obscuring dust, but within it lies a remarkable landscape of stellar nurseries, each one blazing with the light of thousands of young suns. These clusters embody the culmination of the processes that began in the molecular reservoirs transforming cold gas into brilliant starlight. They are the living proof of the galaxy's current state, a system in the midst of forging new generations of stars at a pace unmatched in its history. From here, the exploration continues to the next layer of the narrative, the feedback processes through which these young clusters shape their surroundings, regulating the very activity that gave them birth, and linking the scales of stars to the grand evolution of the Cigar Galaxy. The birth of countless clusters in the core sets in motion a cascade of feedback processes that reshape the galaxy from within. Massive young stars begin releasing intense radiation, almost immediately bathing their surroundings in ultraviolet light that ionizes gas and causes it to glow. This radiation creates expanding shells pushing outward against the surrounding medium. Stellar winds add to this process, streams of charged particles rushing away from the surfaces of young stars at hundreds of kilometers per second. These winds collide with nearby gas, compressing some regions and dispersing others, stirring turbulence throughout the core. Within only a few million years, the most massive stars reach the ends of their lives and explode as supernovae, releasing energy on a scale that dwarfs all previous feedback. Each supernova sends shock waves racing outward, heating gas to millions of degrees and injecting heavy elements into the environment. The combined effect of thousands of massive stars dying in rapid succession transforms the structure of the core, creating bubbles, cavities and filaments of hot gas. These feedback processes operate simultaneously, overlapping and reinforcing one another. Radiation from massive stars maintains ionized regions, stellar winds carve cavities, and supernova blast open new channels. Together they create a turbulent environment where gas is constantly in motion. This turbulence both triggers and inhibits further star formation. In some places, shock waves compress gas clouds, causing them to collapse into new stars. In other places, the same energy disperses clouds before they can collapse, halting star formation. The result is a self-regulating system where feedback ensures that star formation does not proceed unchecked, but instead rises and falls in cycles. One of the most visible effects of feedback in the core is the creation of superbubbles, vast cavities filled with hot gas. These superbubbles form when multiple supernovae explode within the same cluster, their shock waves merging into a single expanding structure. The walls of these bubbles are bright shells of ionized gas, while their interiors glow in X-rays from the million-degree plasma. Some superbubbles grow large enough to break through the disk, venting hot gas into the halo and feeding the galactic superwind. These breakouts demonstrate how processes within small regions can influence structures on scales of thousands of light-years. The energy from feedback also stirs the molecular reservoirs that fuel star formation. In some cases, shock waves compress clouds, triggering the birth of new clusters. In other cases, feedback disperses gas, preventing further collapse. This dual role ensures that star formation remains balanced rather than runaway. Without feedback, the molecular gas would collapse too quickly, producing an unsustainable burst of stars that would consume the available fuel in only a short time. With feedback, the process is moderated, extending the life of the starburst. Chemical enrichment is another key result of feedback. The heavy elements forged in the cores of massive stars are spread into the surrounding gas by stellar winds and supernovae. These elements include oxygen, carbon, silicon, and iron, all essential to the formation of planets and life in later epochs. As they mix into the molecular gas, they increase the metallicity of future generations of stars. Over billions of years, this gradual enrichment transforms the galaxy's composition, ensuring that each new cycle of star formation begins with a richer supply of building blocks. The interplay of feedback and star formation is not confined to the core, but extends outward. Shock waves from supernovae and winds from clusters propagate into the inner disk, disturbing gas and influencing star formation on larger scales. Some regions may be triggered into new activity, while others are cleared of gas and left quiet. This ripple effect demonstrates how feedback couples the fate of the core to the wider galaxy, linking processes across scales from individual stars to the entire system. Observations of the feedback in this galaxy reveal its complexity. Invisible light-glowing filaments trace the ionized shells around clusters. In infrared, warm dust heated by radiation outlines the regions of intense activity. In radiosynchrotron emission from electrons spiraling along magnetic fields reveals the influence of cosmic rays accelerated by feedback. In X-rays, hot plasma fills the cavities created by supernovae, showing the full extent of the energy released. Together, these views present a portrait of a core alive with motion constantly reshaped by the forces unleashed by its stars. Feedback also contributes directly to the galactic superwind. As energy builds in the core, some of it escapes along the axis perpendicular to the disk, driving hot gas outward into the halo. This outflow carries with it the heavy elements produced in the core, spreading them into intergalactic space. The superwind is therefore the large-scale manifestation of feedback, connecting the fate of individual clusters to the evolution of the surrounding universe. For astronomers, feedback processes provide crucial insight into how galaxies regulate themselves. They explain why star formation does not consume all gas at once, why galaxies show cycles of activity, and how matter and energy are exchanged between galaxies and their environments. Without feedback, theoretical models cannot reproduce the galaxies we observe today. With feedback, the balance of processes becomes clearer, showing how self-regulation emerges from the combined effects of countless stars. The violence of feedback contrasts with the calm appearance of the galaxy when viewed from afar. Through a telescope, it appears as a glowing spindle of light, its dust lanes giving it a serene beauty. Yet within its core, thousands of stars are shaping their environment with immense power, driving winds, enriching gas, and altering the course of galactic evolution. This hidden turbulence is the heartbeat of the starburst, a constant cycle of creation and destruction that defines the present state of the system. As the journey inward continues, the focus shifts to the channels through which feedback energy escapes into the wider galaxy. These channels form the backbone of the galactic superwind, the structures that carry the influence of the core into the halo and beyond. In tracing them, one sees how the activity of individual clusters extends its reach across tens of thousands of light years, linking the smallest and largest scales in the life of the Cigar Galaxy. The collective force of radiation winds and supernovae in the core finds its most dramatic expression in the channels of the galactic superwind. These outflows rise from the central regions and carve paths through the dense disk, breaking open into the halo and extending tens of thousands of light years into surrounding space. The channels form where energy released by young clusters aligns along paths of least resistance, often perpendicular to the plane of the disk. Along these routes, hot gas accelerates outward, carrying with it both light elements such as hydrogen and heavier elements forged in stars. The superwind is not a single uniform flow, but a complex system of filaments, bubbles, and cavities that merge into larger streams. Each channel begins as a superbubble in the core, driven by multiple supernovae exploding in quick succession. As these bubbles grow, they press against the disk until they break through, releasing their contents into the halo. Once released, the gas accelerates outward, sometimes reaching velocities of hundreds of kilometers per second. This acceleration is visible in the Doppler shifts of emission lines from the gas, confirming the high speeds at which matter escapes. These flows are hot, with temperatures of millions of degrees Celsius, and they glow in X-rays as a result. Invisible light filaments of ionized gas trace their outlines, glowing with the characteristic red of hydrogen and green of oxygen emission. Infrared observations reveal dust carried outward along with the gas heated as it streams away from the core. Radio wavelengths detect synchrotron emission from cosmic rays spiraling along magnetic fields in the outflows. Together, these observations show that the superwind channels are multiphase structures carrying matter in many forms. The geometry of the channels is shaped by the distribution of gas and dust in the disk. Where the disk is thinner, the outflows escape more easily, producing wider filaments. Where the disk is thicker, the gas must force its way through, creating narrower, brighter features. Magnetic fields add another layer of structure, guiding the flows and helping to maintain their coherence over large distances. The result is bipolar outflow, with opposing plumes extending above and below the disk. These plumes are among the most striking features of the galaxy, stretching far into the halo and marking the scale of feedback from the core. The material carried by the superwind is enriched with heavy elements. Oxygen, carbon, nitrogen, and iron produced in the cores of massive stars are expelled into the halo and beyond. This enrichment alters the composition of the intergalactic medium, ensuring that future generations of stars forming in the vicinity will have access to heavier elements. In this way, the galaxy contributes directly to the chemical evolution of its environment, seeding space, with the products of stellar nucleosynthesis. The superwind also removes gas from the galaxy, regulating its future star formation. By expelling material, the outflows limit the amount of gas available per new stars, ensuring that the starburst does not consume all its fuel too quickly. This self-regulation is a key aspect of galactic evolution, balancing the inflow of gas from the bar and halo with the outflow driven by feedback. The channels of the superwind therefore represent both the release of energy and the regulation of star formation. Their effects extend far beyond the core, influencing the structure and destiny of the galaxy as a whole. The visual appearance of the superwind channels is dramatic. In long exposure photographs, they appear as glowing red plumes extending outward from the center, like fire rising from a furnace. Yet this appearance is not decorative. It is a direct manifestation of ionized hydrogen lit by the ultraviolet radiation of the core. The filaments within the plumes twist and curl, shaped by turbulence and magnetic fields. Their motion is not smooth but chaotic, with eddies and shocks marking the interaction of hot and cooler gas. These details provide evidence of the complex processes operating within the outflows processes that continue to challenge models of galactic winds. The energy carried by the superwind channels is immense. Estimates suggest that the total power is comparable to that released by thousands of supernovae every million years. This energy is sufficient to lift enormous masses of gas into the halo, and even beyond the gravitational pull of the galaxy. Some of this material will escape entirely, joining the intergalactic medium. Some will fall back in a galactic fountain, cooling and raining down onto the disk after millions of years. Either way, the circulation of matter ensures that the galaxy remains connected to its environment. Observations of other galaxies show that superwinds are a common feature of intense starbursts, but in this nearby system, the details are more accessible. The Cigar Galaxy has become a reference point for understanding how such outflows operate, providing insights into processes that were far more common in the early universe. Billions of years ago, galaxies frequently experienced starbursts and superwinds, and their feedback helped shape the large-scale structure of the cosmos. By studying this local example, astronomers gain a clearer picture of how galaxies evolve across cosmic time. The superwind channels also illustrate the connection between small-scale and large-scale processes. The death of individual massive stars drives shockwaves that merge into superbubbles. These bubbles combine to form channels that extend tens of thousands of light-years. In this way, the life cycles of stars, measured in millions of years and light-years, influence the structure of the galaxy and even the composition of intergalactic space. The channels are therefore bridges across scales, linking the fate of stars to the destiny of the cosmos. To the naked eye through a telescope, the galaxy appears as a narrow spindle, with dark dust lanes serene and silent. Yet hidden within is a torrent of energy rushing outward through vast channels, invisible in ordinary light but revealed by instruments across the spectrum. These channels are the arteries of the starburst, carrying matter and energy outward in a continuous flow. They remind us that galaxies are not static, but living systems reshaped constantly by the forces within. As the journey continues inward, the next focus turns to the tools that reveal these hidden processes. Infrared and X-ray views of the galaxy provide windows into the obscured core and the blazing outflows, showing details that ordinary light cannot capture. By examining these wavelengths, astronomers uncover the full extent of activity within the Cigar Galaxy. The true nature of the galaxy's starburst activity is revealed not in visible light, but in the invisible wavelengths that penetrate dust and uncover hidden structures. Infrared observations are among the most powerful tools because dust grains that obscure starlight in optical wavelengths glow strongly when warmed by radiation. In infrared images, the core of the galaxy shines with exceptional brightness, outshining the calmer spirals of its local group. The glowing dust highlights the regions where clusters of newborn stars are embedded in thick clouds invisible to optical telescopes. These observations demonstrate that what appears dark and mottled in visible light is in fact blazing with concealed energy. Farther out, the dust lanes that cut through the disk also glow in infrared, showing how heated material traces the flows of gas channeled inward by the bar. The bar itself is clearly visible in these wavelengths lined with streams of dust warmed by starlight. Infrared maps also reveal the distribution of molecular gas, since carbon monoxide emits at sub-millimeter wavelengths that can be traced by sensitive instruments. These data confirm that the core contains vast reservoirs of star-forming material packed into a compact region where activity is most intense. Alongside infrared X-ray observations provide a complementary view. Where infrared shows the cool and warm phases of gas and dust, X-rays expose the hottest and most energetic regions. The galactic superwind channels glow brightly in X-rays, their million-degree plasma emitting high-energy radiation as it escapes into the halo. X-ray maps also reveal superbubbles within the core, vast cavities carved by supernova explosions and filled with hot gas. These structures, invisible in ordinary light, demonstrate the immense power released by the feedback of massive stars. The distribution of X-ray emission traces the pathways by which energy escapes from the core, linking the feedback of individual clusters to the large-scale outflows. Together, infrared and X-ray images build a picture of the galaxy as a system alive with energy at every wavelength. Infrared shows where stars are born hidden in thick dust, while X-rays show where stars die, their explosions heating gas to extreme temperatures. Optical light fills in the middle, displaying the starlight itself and the glowing filaments of ionized gas. Radio wavelengths add yet another layer, mapping the cold hydrogen and tracing the synchrotron emission from cosmic rays moving along magnetic fields. The galaxy therefore appears differently depending on the window through which it is observed each wavelength, uncovering a different aspect of its activity. Infrared images also allow astronomers to measure the total rate of star formation with greater accuracy. Because dust absorbs much of the visible light from young stars, optical measurements underestimate the true rate. Infrared, by contrast, captures the re-radiated energy from dust, providing a more complete measure. These observations confirm that the galaxy is forming stars at a pace far beyond that of the Milky Way, converting several solar masses of gas into stars every year. This extraordinary rate is sustained by the continuous inflow of gas along the bar as revealed by radio maps. X-ray data provide insight into the fate of gas expelled by the core. The hot plasma seen in X-ray images extends thousands of light years into the halo, showing that the superwind channels are carrying material far from the disk. The temperatures are so high that the gas cannot cool quickly, ensuring that much of it will escape into intergalactic space. This mass loss influences the future of the galaxy, reducing the supply of gas available for star formation in later epochs. At the same time, it enriches the surrounding environment with heavy elements contributing to the chemical evolution of the group. Infrared and X-ray views also highlight the connection between small and large scales. Infrared shows the dense cores of molecular clouds only a few light-years across where stars are forming today. X-rays show the vast filaments extending tens of thousands of light-years where the results of those stars' lives are carried outward. By combining these observations, astronomers can trace the entire cycle of matter, from cold gas collapsing into stars to hot plasma escaping into the halo. The galaxy becomes not a static object, but a dynamic system where energy flows across many orders of magnitude in scale. Observations in these wavelengths have been made with some of the most advanced instruments ever built, including space telescopes that operate above Earth's atmosphere. Infrared light is largely blocked by water vapor in the air, while X-rays are absorbed completely. To see the galaxy in these bands, telescopes must orbit beyond the atmosphere, providing a clear view of the universe. Data from these instruments have transformed understanding of the galaxy, revealing details that ground-based telescopes could never detect. The multi-wavelength picture that emerges is one of remarkable complexity. No single view tells the full story. Only by combining infrared, X-ray, optical, and radio can astronomers see the galaxy as it truly is, a system where cold gas, warm dust, hot plasma, and cosmic rays interact in a continuous cycle. Each wavelength adds to the narrative, showing that the starburst is not confined to one layer, but permeates the entire structure. To human eyes, the galaxy remains a narrow spindle with dark dust lanes. Yet in the invisible spectrum it becomes a blazing furnace, pouring out energy across the electromagnetic spectrum. This dual nature underscores the importance of looking beyond what can be seen, of probing the hidden layers of reality with instruments designed for each kind of light. By doing so, astronomers uncover the true scale and intensity of the processes shaping the galaxy. These observations also allow comparisons with more distant starburst systems. Galaxies in the early universe often underwent similar phases, but they are too far away to study in detail. By examining this nearby example with the full range of wavelengths, astronomers can infer what was happening billions of years ago when starbursts were more common. The galaxy therefore serves as a local analogue of cosmic youth, a window into the processes that shaped much of the universe's history. As the exploration continues, the next step is to place the starburst into a broader temporal framework, the cycles of activity, the balance of inflows and outflows, and the gradual enrichment of matter all contribute to the long-term evolution of the system. By looking at the starburst life cycle, astronomers can see how the Cigar Galaxy changes across millions of years, moving from one phase to another in a continuous process of transformation. The story of this galaxy cannot be understood without considering the starburst life cycle, a sequence of phases that governs how activity rises, peaks, and eventually subsides. Starbursts do not last indefinitely. They are temporary states triggered when conditions channel enough gas into the central regions to ignite rapid star formation. In this system, gravitational encounters within the M81 group disturbed its disk funneling gas inward along the bar. That inflow created the dense molecular reservoirs that now feed the central clusters. The present state is therefore a product of both internal dynamics and external interactions, a phase that began millions of years ago and will eventually give way to something quieter. The current burst of activity is marked by extraordinarily high rates of star formation, with several solar masses of gas converted into stars each year. This pace is sustainable only because inflows continue to supply the core. Over tens of millions of years, however, the molecular gas will be depleted. Stellar feedback will also play a role, driving much of the gas outward in superwinds. When the supply of fresh gas runs low, the rate of star formation will decline. The galaxy will transition into a calmer state, with fewer new clusters forming and the superwind weakening. Such a decline does not mark the end of star formation altogether, but rather a shift to a lower level, more like that seen in the Milky Way. The cycle of inflow, starburst, and decline may repeat many times over the life of the galaxy. Each encounter with a neighbouring system can disturb the disk anew, sending another wave of gas into the core. Each cycle adds to the cumulative enrichment of the galaxy, raising the metallicity of its stars and altering the balance of populations across its disk. In this way, the starburst life cycle is not a singular event, but a recurring process shaping the long-term evolution of the system. During the peak of a starburst, the effects are visible across all scales. The core glows in infrared as dust is heated by young stars. The superwind channels shine in X-rays as hot plasma streams outward. The disk is stirred by turbulence, and the halo is enriched with heavy elements. These features are transient but powerful, leaving lasting marks even after the burst subsides. For example, enriched gas expelled into the halo will eventually rain back down, altering the composition of future star-forming clouds. Stellar clusters born in the burst will survive for billions of years, orbiting the core long after the event has ended. The traces of today's starburst will therefore remain imprinted on the galaxy's structure and populations for cosmic timescales. The regulation of the starburst is an essential part of the cycle. Without feedback, gas would collapse too quickly, producing a single unsustainable burst that would consume the reservoirs in a few million years. With feedback, the process is moderated, stretching the burst across tens of millions of years. This regulation ensures that the galaxy does not exhaust itself too quickly. Instead, it balances inflow and outflow, creation and destruction, in a dynamic equilibrium. Observations of this system allow astronomers to study this balance in detail. They can measure the inflow of gas along the bar, the rate of star formation in the core, and the outflow of gas in the superwind. By comparing these rates, they can see how the cycle sustains itself. The lesson is that galaxies are not static, but constantly shifting, moving through phases of activity and quiescence, each phase leaving behind enduring consequences. The life cycle of a starburst also has implications for the larger universe. In the early epochs of cosmic history, starbursts were common, triggered by frequent interactions among young galaxies. The processes seen here today were once widespread, shaping the distribution of stars, the enrichment of the intergalactic medium, and the growth of galactic structures. By studying a nearby example, astronomers can reconstruct what happened billions of years ago on much larger scales. This system therefore serves as both a local laboratory and a cosmic analogue. Over time, the starburst will fade, but its influence will persist. The clusters formed during this phase will remain as dense stellar systems orbiting the galaxy. The heavy elements expelled into the halo will mix with future inflows, enriching the next generations of stars. The galaxy itself may encounter new companions, triggering fresh bursts in the distant future. Its story is one of cycles, each burst a chapter in a long narrative of transformation. For now, the galaxy stands in the midst of one of its most active periods, a vivid example of how gravitational interactions and internal dynamics combine to ignite intense creation. To observers on Earth, it is a narrow spindle of light set against the dark sky. To astronomers with instruments across the spectrum, it is a furnace of activity, forging stars by the thousands and reshaping itself with every passing million years. This moment in its history is temporary, but the traces it leaves will endure across cosmic time. With the starburst life cycle placed in context, the inward journey reaches its conclusion. From the halo to the superwind, from the dust-rich outer disk to the dense bar, from the molecular reservoirs to the blazing clusters, every layer of the system reveals the interconnected processes that define it. The Cigar Galaxy is not a static object, but a living system caught in a phase of extraordinary activity that will fade yet echo across its future.